Hi, welcome back to es346 Basic Thermodynamics. This is module 6.3 on refrigerators and heat pumps. The section in the textbook is 6.4. Here are the three learning outcomes for this module. At the end, you'll understand the basic characteristics of refrigerators and heat pumps. You'll be able to differentiate between a refrigerator and a heat pump, and you'll be able to quantify the efficiency of refrigerators and heat pumps. So first, let's go ahead and talk about what is a refrigerator. And this is a less abstract concept than that of a heat engine, because we're all pretty common with a refrigerator, and most of them have them at home, probably a vapor compression refrigerator. The refrigerator has four basic components. It's got a compressor that it goes ahead and accepts some energy or work input. It compresses a working fluid. This refrigerant is usually something like R134A or some other refrigerant. It pressurizes it to a high pressure, pH, and it also goes up to a higher temperature, TH, during that compression process. Then it will cool it off in a condenser, and it's going to get colder, and the main thing is it's going to go ahead and turn into a liquid. And so on this side over here, it becomes something similar to a compressed liquid. In order to do that, it rejects some heat to a high temperature sink, which is QH. Then it's going to go ahead and run through a throttling valve where the temperature is going to drop, so now I'm going to have TL. And at this point, we go through the evaporator, which is the freezer box or refrigerator. This can go ahead and absorb energy from a low temperature source, which is QL, and then it goes ahead and continues to run through that cycle. So when we talk about the efficiency of a refrigerator, we tend to use the term coefficient of performance in place of efficiency, but they mean the exact same thing, or it's often abbreviated COP. And so if I have a refrigerator over here, as we said, electrical work comes in, QL comes from my low temperature, T sub L, and then energy is rejected to the high temperature, TH. And so if we write our coefficient of performance, COP, it's defined the same way as efficiency, is that it's whatever is desired over whatever is required. So what is desired from a refrigerator? Well, what we want is this value of QL. This is what keeps things cold. So the desired is QL, and what's required is we have to plug it in. And so that's W. So there's my coefficient of performance of a refrigerator. Now let's go ahead and apply the first law to my refrigerator. I'll put an R in there. All the components are inside that circle. And we know that the energy that goes in is the energy that goes out. So looking at the arrows that go in, I have W plus QL equals QH. And I can go ahead and rearrange that to W, and W is equal to QH minus QL. Now I'm going to go ahead and take this, what I've solved for W, and put it into this equation up here for my coefficient of performance. So COP is going to be QL over QH minus QL. And if I divide through by QL, just to get it in a little different form, I'm going to have 1 over QH over QL minus 1. And that's the coefficient of performance for a refrigerator. Now, if we talk about heat pumps, they're very similar to refrigerators, if we look at what the components of them are. And so here's the way they look. They also accept electrical work, and there's going to be a low temperature T sub L down here where QL comes in QH. So when we saw the refrigerator, we saw that QH is always greater than W. And in fact, what we were doing is we're sort of leveraging the work that we put in order to get more energy up here with QH. And so you can imagine I could go ahead and instead of running an electrical resistance heater in my house, what I could do is I could just stick a refrigerator in the wall so that the heat coils on the inside of my house. And so what would happen is I would plug this in, put in a certain amount of work, W, but I'm leveraging it, and so some QL is going to come in here, turn into QH, and go into my house. And so effectively, I'm going to get more heat out than I'm putting in work. And that sure seems pretty nice. And that's the concept of a heat pump. And so, although they don't look like this, their thermodynamic description is the exact same as that of a refrigerator. This is actually what heat pumps look like in reality. And these down over here, this is essentially your freezer box. This is where the QL is coming in. And normally we go ahead and bury these in the ground because that's a really good thermal reservoir source down there. So it's going to go ahead and absorb energy, and then it's going to dump it into my house, which is at QH, and I'm going to go ahead and have to power this device. So the only difference really is that I've got all these coils that I've buried in the ground. Sometimes they're vertical, as shown in this diagram. They could be horizontal, depending on how easy it is to dig. And if you are lucky enough to have a water source nearby, that's actually a really good thermal reservoir as well. The devices themselves look a lot like an air conditioning unit because they essentially are. And this is what they look like sitting outside a house. And this is what a heat pump would look like. So let's go ahead and determine what the coefficient performance is for a heat pump. It's going to be a little different than a refrigerator. So although the basic components are the same, I have work coming in, QL coming in, and QH going out. But now I'm going to go ahead and determine what's the coefficient of performance. And that's going to be, again, whatever is desired over what's required. But now, however, I'm going to put a little HP here because this is the coefficient of performance of my heat pump. What's actually desired is I'm trying to heat my house with it. So I really want QH. So the desired is QH, and the required is the work. So let's do our energy balance again. We just did it again on the previous slide, but it's always good practice to do it again. Energy in is energy out. The arrows going in are QL plus W is equal to QH, or solving for the work. The work is going to be QH minus QL. And now I'm going to go ahead and put that into this equation up here. So the coefficient of performance of my heat pump is QH over QH minus QL, or I can divide through by QH, and I have 1 minus QL over QH. And that's the coefficient of performance of a heat pump. And what we'll see, and you can actually do the algebra if you want, the coefficient of performance of a heat pump is the coefficient of performance of a refrigerator plus 1. And effectively that's because, remember again from this idea of leveraging, is that the lowest value of the coefficient of performance per heat pump I could have would be 1. That would be the minimum value. That would be that this number is effectively 0 and all the work is turning in to QH. Well, if I had a coefficient of performance, my heat pump, which was equal to 1, the coefficient of the performance of the same refrigerator would be 0, which makes sense because I just said it's not bringing any QL, so I'm not getting anything out of it. The lowest value would be 1 for a heat pump. The lowest value would be 0 for a refrigerator. Refrigerators are often rated, if you go and buy them at the store, by something called the EER, which is the energy efficiency rating. And it's related to the coefficient of performance, but it's defined a little bit different. And so I kind of want to review what it is. You often see these little energy guides. In fact, they're required by law on refrigerators to tell you what their EER is. Well, the EER is defined as, it's similar to desired over required. It's going to be QL over work, the desired over the required, but it's reported in some strange units. It's reported in the units of BTUs over watt hours. So kind of this mixture of English and SI units. And so if you have an EER of 1, that means that for 1 BTU of QL, it requires 1 watt hour. Well, let's go ahead and figure out how that's related to the coefficient of performance that we just defined or derived. So 1 BTU, to go ahead and convert this into SI units, is 1055 joules, which is also 1055 watt seconds. All right. And so let's imagine I had an EER of 1. Now, with EER of 1, that means that 1 BTU would be 1055 of joules. So I can do my coefficient of performance of my refrigerator, which we said is QL over W. And if the EER is 1, I'm going to get 1055 joules over, this is over watt seconds, excuse me. Watt hours, and if I multiply that by 3600, I can get that into watt seconds. And so that number right there is 0.293. So that says, so for a value of EER of 1 is the same as the coefficient of performance of 0.293. So let's look at what's the coefficient of performance of this device here, which was 13.3. Well, I take 13.3, multiply it by 0.293, and that right there is 3.9. So that's the coefficient of performance of this refrigerator. Let's go ahead and do a numeric example. And so I have a refrigerator. I see that its EER is 12. And I want to go ahead and cool a 6-pack of beverages from 25 degrees Celsius down to 5 degrees Celsius. And I want to know how much energy this is going to go ahead and use. So here's my coefficient of performance for my refrigerator. And we just saw from the previous one, if I take my EER of 12 and multiply that by 0.293, I get 3.55. And remember that the way this is defined for refrigerators is just QL over W. And so what I'm trying to find is the work that goes in, and what I know is 3.55, and so I'm going to have to figure out what QL is. Well, I'm taking 12 beverages and I'm cooling them this 25 degrees to 5 degrees. So QL, we can now use the first law, which we know is M CP delta T. So this is a liquid and incompressible material. So we can go ahead and figure this out. I have 6 beverages. Each one weighs about 0.355 kilograms, 355 milliliters. We're just approximating this as a liquid. The CP of liquid is water is about 4.18 kilojoules per kilogram degree C, and we're going to multiply that by its delta T, which is 20 degrees. So I find out that if I do that arithmetic, my QL is 178 kilojoules. So now I'm going to go ahead and figure out the amount of work by putting it into this equation right up here, where I see now that my work is going to be QL over 3.55. So 178 kilojoules divided by 3.55, and then that amount of work is going to be 50.2 kilojoules. So I only need to put in 50.2 kilojoules in order to remove 178 kilojoules of energy from my beverages. So there's a couple classic statements of the second law of thermodynamics, and I want to go through both of those with you now. Here's the first one due to two people, Kelvin and Planck, and it says, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Now I'm going to go ahead and give you another classic statement. This one is from Clausius, and it says, it's impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a higher temperature body. Both of those sets of researchers came up with those statements independently, and they're both statements of the second law of thermodynamics. And we can kind of look at them in this diagram here and see where they're actually equivalent. So here what I have is I have a TH and a TL. I have my two reservoirs. And here, over here, I have the Kelvin-Planck statement that says I can't go ahead and receive energy and produce work without dumping anything to the low temperature. And over on the right-hand side, I see what I've got is a device that is getting energy here, just like my classic heat pump or refrigerator, and a work input. So let's go ahead and put a couple numbers in here. So just for giggles, let's go ahead and say we have 50 kilojoules coming down in this direction right over here. And, maybe we have 100 of energy going up in this direction right here. And so if the 50 is coming down, that means that I have to do 50 in this purple arrow, and 50 and 100 is going to be 150 going up in that direction. Well, now let's go ahead and draw the equivalent system. So I'm going to go ahead and combine both of those together and see what it looks like. Well, I've got this 100 that is coming from, those joules coming from T low, and I have 50 going down and 150 going up, which gives me a net 100 kilojoules going up here to T high. And what I see is I have this device where energy is just going from something cold to something hot, and it doesn't require any work. And that's the statement from Clausius. And so I realized that the Kelvin-Planck statement and the Clausius statement are equivalent. And what the second law is really saying is simply energy doesn't go uphill. Energy only goes downhill. We notice that. Things that are hot get cold. Things that are cold don't spontaneously get hot.